I'm going. Okay, so welcome to the Tutte Colloquium today. So we're very happy to have Cecile Pierrot talking. She's, I think, graduated in 2016 from University of Panthéon-Sorbonne in Paris. And now she's a researcher in the French National Institute in India. So Cecile works in public cryptography and discrete logarithm, and she's going to talk about something about discrete logarithm, I think, in finite fields today. So take it away, Cecile.
I have lost my mouse. Sorry. Again. Oh, okay, good. Do you see my slides on that?
Yes.
Good.
Thank you.
It's working. Sorry for the problem. So thank you a lot for the invitation. I wish I could be with you, but I'm still very happy to give this talk about discrete logarithm in my kitchen. So discrete logarithm is a very useful tool in cryptology, as we will see in a few minutes. I will try to keep my talk at a high level so that anyone can catch something new. So don't be afraid if you know nothing about crypto. And well, in the meantime, for the few insiders, I will give new ideas at the end, but you will need to wait for the end. So the problem I'm the most interested in comes from cryptology, which is, as you may know, the study of techniques for secure communication in the presence of third parties. Sometimes we make the difference between cryptography, which is, let's say, the art of creating codes, and cryptanalysis, which is the art of breaking them. So it's not a big issue, and most of the time I will just say crypto. So when we talk about crypto, we usually think of the military environment, but today the main applications are in the civil area. So cryptology is used, for instance, in passports, in when you plug your card into a point of sale terminal, it communicates with your bank in a secure manner. There are also many applications today that allow you to send encrypted messages through your phone, like WhatsApp. I don't know if you have Telegram and Signal in Canada, but I'm pretty sure you have WhatsApp. When you go on the internet, you use crypto too. And because you are living in Canada, you may be, I'm not sure you are, it depends maybe on your province, but you may be concerned by e-voting too. So here is e-voting. Well, the aim for the sender and the recipient in crypto is to ensure mainly three items. There are others, but mainly three, the three one like that. So first, confidentiality. It means that the eavesdroppers, that are my people in the middle here, they must not be able to understand the message. Then you have what we call integrity. If someone modifies the transmission, then the recipient will note it. And finally, you have authentication. That means if the sender is not the one that is supposed to be, then again, the recipient notes it. So for example, confidentiality has been guaranteed for centuries by what we call secret key cryptography. And a very common analogy to understand the process is as follows. So let's say the sender wants to send a message. She put the message in a box. She closed the box with a lock, and then she sent the box. And the recipient is able to open the box and read the message as soon as he shares a copy of the same key. But the question is, how should they do if they have never met? Is this common key mandatory or not? Oh, by the way, this is called secret key crypto, but it's the same to say symmetric cryptography because both the recipient and the sender has this common key. So what they do is somehow symmetric. So sadly, you see that the two entities must have exchanged this common key beforehand. And actually, this is a major issue because the key through the centuries. So first you can think of it just at the beginning, like just a function that sends a letter to another one. So you can say that every B are going to be E, every C are going to be F. It's a very, very simple and old way to encrypt a message, but still. So here the key is just this way to this alphabet. So you can think about that, or it was just a simple password, or today it's just a numerical data, like a sequence of bits. So the fact is, how do we make this data go from the sender to the recipient? And finally, we came back to the initial problem. So I guess you see that it's the same problem. The sender wants to send a message, but she needs to send beforehand a key. So it's the same problem. And cryptographers were stuck on this question for ages until the end of the 70s, the late 70s, when Diffie and Hellman proposed a key exchange protocol. And we will see what is that key exchange protocol in a few minutes. There was another way to solve the problem that was proposed by Rives, Shamir, and Edelman months or year later. So here is that idea. So going back with the analogy, the idea is that the recipient only has a key associated with a lock. And when the sender wants to write a message, she asks for the open lock. Again, she put her message in the box. She closed the box, but without any lock here. Yeah, without any key, sorry. And she sent it back to the recipient that is able to read the message with his own and unique secret key. So all these methods, whether it's key exchange or what I just presented, it is what we call public key cryptography, and it's the same as saying asymmetric key crypto, asymmetric crypto. There is a typo on my side. So in a nutshell, we have two types of cryptography: secret key and public key. Secret key is the one that we have done for the past 2000 years. It is nice because it is fast and it deals with small keys. So for instance, 100 or 200 bits keys are enough for secret key cryptography, but it needs a key exchange beforehand. Just a name, an example. So AES, that stands for Advanced Encryption Standard, is the protocol that is mainly used in the symmetric key area. And on the other hand, you have public key crypto, that is far more recent, as you can see. It does not need any preliminary exchange of data, so that is really good, but it is slower and it uses larger keys. So for instance, we encounter 2,000 bits keys here in this world. We'll talk about some names later, but you can remember the RSA protocol. And I'm just going to talk about Diffie-Hellman, so we'll see about Diffie-Hellman. So this talk is about public key crypto, but in practice, keep in mind, so for instance, with PGP, that is an encryption software, in practice, we start with a key exchange most of the time, and then we switch to secret key crypto to have the advantage of both worlds. So we have a hybrid system. The amazing and yet very simple idea proposed by Diffie and Hellman is the following. Take a multiplicative group, big G, with a generator, so it's a cyclic group, and both the group and the generator should be public. So then, the people that want to communicate create their own secret element. It's just an integer, so here A and B, but A and B are secret. And they compute the generator to the power their secret integers. So G to the A and G to the B. And then they send the result. So one is sending G to the A while the other is sending G to the B. And after that, they take what they have received and they compute it to the power of their secret integer. So on one hand, you have G to the B to the A, which is equal to G to the AB. And on the other, you have G to the A to the B, which is also equal to G to the AB. So this is their secret common key. Their common key is going to be this G to the AB. And they got it without sending it, so it's not public. You can see that the security of this protocol relies on the computational Diffie-Hellman problem, which is the following. Knowing G to the A and G to the B, so the public elements, try to find the secret element, which is G to the AB. You can see that it's not the same, but it is sufficient to be able to recover A just knowing G and G to the A. Why? Because if you know G to the A, and if you know how to recover A, then you have A and G to the B, and you can recompute G to the AB thanks to G to the B to the A. So what does that mean? It means that this is the problem we are going to be interested in, and this is the discrete logarithm problem. So let's reformulate a bit. You take a group, big G, with a generator, little g, so it's a cyclic group. And we say that we solve the discrete logarithm problem in big G if we are able to invert this map. So it means that for any arbitrary element, and I underline the fact that it's for any arbitrary element, you should be able to recompute an integer x such that G to the x is equal to h, your arbitrary element. This is supposed to be a one-way function, so it is hard in general. I say in general because the complexity of the various algorithms designed to solve it depends on the group you are considering. So in crypto, we use in practice two different kinds of groups for G, either a finite field, and we will talk a lot about finite fields, or the group of rational points of an elliptic curve. So for instance, I don't know if you see it, but on my ladder, you can see that in the group of rational points of an elliptic curve, the problem of finding a discrete log is as hard as in a generic group, almost as hard. So in this talk, we are looking at discrete logarithm fields. You have inside finite fields some with what we say a small characteristic that are broken, and you have other finite fields with medium or large characteristic. And I will say some word about that if you are not familiar with it. So those finite fields I will focus on quite a lot, and they are considered to be still hard. So the discrete logarithm problem is a hard problem. But if you still want to try to solve it, you have two algorithmic point of view. You can try to apply a generic algorithm that applies for any group. Usually you only need to know the factorization of its order. So for instance, you have algorithms called Polaro, baby step, giant step, if you know them. Or you can try to use some extra data you have to design a specific algorithm to your target. So to target finite fields, as you can see with the little drawing here that just appeared, we are helped by a family of algorithms called index calculus. But before going further, I'm not sure if finite field is clear for everyone. So I'm really sorry if it is, but if it is, we will have a short recap. So it's a short recap of a particular case that you probably know that are prime fields, prime finite fields. So it's something very easy. Take just a prime P, choose your favorite prime, and look at all the integers modulo that prime. We write it Fp, so it's the finite field with P elements. So for instance, if I choose 7, because it's small, so it's easy for the computation, here is my finite field. So you see it's quite easy. And I pretend that 3 is a generator of F7 without looking at 0. So 0 is not there. What does that mean? It means that, so here are all the elements of my finite field without 0. If I start from 3, and if I multiply 3 by itself, I get 3 times 3, which is equal to 2 mod 7. If I do it again, if I take my results, so here 2, and if I multiply it again by 3, I get 2 times 3, which is 6. This one is easy. So I have 6. And then again, 6 times 3, it's 18. 18, it's 14 plus 4. So it's 4 modulo 7. Yes, it's 4 modulo 7. And then again, I take 4, I multiply it by 3. I have 12, which is equal to 5 mod 7. And then I get 1, and I go back to 3. So we say that 3 is a generator because if you look at all the powers of that precise element, you are able to describe all the elements of your group. By the way, let's compute the first discrete log. So my question is, what is a discrete logarithm of 6? So it means that you should be able to find an integer such that g to that integer is equal to 6 mod 7. And if you have a good memory, maybe you remember that it's 3. So if you know it, you have calculated your first discrete logarithm. So congrats. This one was easy. The one that will follow, maybe not. But I think it's always good to start with an easy example. So I'm not talking about prime finite field because it's easy to explain, but also because they are maybe the ones that are the most deployed in crypto. Maybe because it's easy to work with, but it's really something we see in the wild. So what about finite fields? Well, you can see finite fields as a generalization of that idea thanks to polynomial. So instead of looking at integer modulo an integer, you are going to look at polynomials with coefficients in Fp, now that you know who is Fp. And all those polynomials, you look at them modulo a special degree n polynomial. That is irreducible, but I'm not talking about that right now. So this is Fp to the n. So you look at polynomials modulo polynomial, a polynomial, and you get a finite field. And n here is just the number of elements in the field. And I just need a short definition. We say that P, this prime, that is quite special here in my finite field, this is the characteristic of the finite field. And why is it interesting to look at the characteristic? Because it says a lot about the hardness, about the complexity of the algorithm. So to evaluate the complexity of an algorithm that solves the discrete logarithm problem on a finite field of order p to the n, like that one, the relevant parameter is essentially the size in bits of the object it takes as input. So here, this is of the order of log p to the n. And studying the relative size of log p, that is here, and the size of the target field, finite field, so log p to the n, allows us to identify three areas. If log p carries more than 2/3 of the bits, then we say that we have a finite field with a large characteristic. So you have two examples there. When you look at the prime field, there is no extension, so everything is in the characteristic, so you have a large characteristic finite field. It's the same if the extension n is equal to 2, 3, 6. It's small enough so that everything is almost in the characteristic, so fp to the 3, for instance, is also a finite field with a large characteristic. When log p carries between 1/3 and 2/3 of the bits, then we say we have a medium characteristic finite field. So again, you have an example there of what could be a medium characteristic finite field. And for sure, if log carries less than 1/3, you have a small characteristic finite field. And we are happy because, for instance, with that definition, those two finite fields with characteristic 2, 3, they are small characteristic finite fields. So everything is fine. Now, what about the algorithms? If you look at medium or large characteristic finite fields, the best algorithms actually that we know to solve the discrete logarithm problem is called the number field sieve. Actually, we have a lot of variants. We will see some later. And it is a sub-exponential time complexity. And maybe you can see it with my drawing, it's a little bit harder to compute a discrete log in a medium characteristic finite field. And then on the other side, you have when the characteristic is small, we know how to design quasi-polynomial time algorithms. So here, it is the reason why those finite fields are considered to be broken and should not be used. Just a few words about small characteristics, really a few words, so that you know if you are not aware about it. So this is the current largest finite field where a discrete logarithm has been found. So it's really huge. It's a finite field with 30,000 bits, and believe me, it's huge. It was achieved last year, and it took about 300 core years to find a discrete logarithm in it. And for sure, all the algorithms are parallelized because, I mean, it didn't take, well, 300 core years is quite a lot, so I'm pretty sure you know that it's parallelized. A word about the size. So I said that for me, it's really a huge finite field, but the fact is, it means that we are now able to break parameters that for other systems are considered to be safe. So maybe you do not know it right now, I guess, yes, no. But for, let's say, large characteristic finite fields or for factoring, the key sizes are about 2,000 or 4,000 bits, but not as large as the one that is broken in small characters. So for this reason, the problem of the discrete logarithm in a small characteristic finite field has to be completely avoided. So let's focus on something that is really hard, still hard, large characteristic finite field. I would like to explain to you the methods used to obtain two record computations. The first one is that one. It was done by some colleagues. Most of them, or some of them, are in my team in Nancy. And it was done last year on a prime field. So here there is no extension degree. It means that n is equal to 1. And the prime is roughly 800 bits. So quite a large problem. And the other one, it was done with my PhD student and another colleague, again in Nancy, on a finite field with, that time, an extension degree, which is equal to 6. So it's slightly smaller finite fields. It has 500 bits finite field, but still it's larger than the previous field on the same shape, so fp to the 6, where a discrete logarithm was found before, and it was last year. And these two computations uses two variants of the same algorithms, the number field sieve. So I guess now it's time to really do math and to have a look at this number field sieve algorithm. I hope you're still there. So the best part is starting. All index calculus algorithms revolve around the same steps. So index calculus, as I said, is you can see it as a family of algorithms. They can do a lot of things. For instance, you have some algorithms belonging to the index calculus family that are able to factorize a large integer. But here I'm just going to talk about my purpose. So that was typo again. I want to find a discrete logarithm in a group, and here my group is a finite field, fp to the n, and keep in mind that p somehow is large. So a large characteristic finite field. So the first thing you have to do if we want to compute a discrete log is to tell how to construct the field. It's not something always easy when the field is just fp as it is, but sometimes with fp to the n, you need to really think about the best way to represent your finite field. And then, so you have 3 steps in all the index calculus family. The first one is the relation collection. So the aim here is to create a lot of multiplicative relations between some specific elements. And those elements, they are small in some sense. So it's a small set of small elements, and this small set, we call it the factor basis F in my drawing. So what does that mean? Let's assume we have one multiplicative relations. It means that we have one equality between products of elements gi to the ei, where gi are elements of my factor basis and ei are known integers. So let's assume I have something like that. What I'm going to do is I'm going to divide by the right member so that I obtain a product of gi to some integers that is equal to 1. And I can take the discrete, the logarithm of that equations, and I have that a sum of integers, and I know that those integers times the discrete logarithm of my factor basis elements is equal to 0. So this is what? This is a linear equation. So at the end of the relation collection, I hope to have enough, or I mean at least a lot of linear equations where the unknowns are the discrete logarithm of my factor basis element. Something I had not said about, but it's written, is the fact that all the equations are sparse. What does that mean? It means that inside one relation, usually you only have a very few numbers of factor basis elements that are there. Most of the time, you just have 0 for the exponent. So for that reason, you are able to write a lot of linear equations, which means you are able to write a matrix of relations, and you perform a linear algebra step to be able to find all the discrete logarithms of the factor basis. And what is nice here is the fact that because we have sparse relations, our matrix is sparse, and we are able to use specific linear algebra that is quadratic and not cubic. So it's much more faster because of the fact that we have sparse relations. And then we have not finished because we have a lot of discrete logarithms, but you need to remember that solving the discrete logarithm problem is being able to recompute or to find a discrete log of any arbitrary element. So we have not finished. And the last step is there for that reason. So it is called the individual discrete logarithm step. And here the aim is to find the discrete log of this arbitrary element h. So how should we do? How could we do? The idea is to try to write this h as a product of small elements in some sense. And then with those small elements, you write them again as smaller elements, as a product of smaller elements. And again, until you reach the factor basis. Because those elements inside the factor basis, remember that they are supposed to be, in some sense, small enough. So here you are very happy because if you take the log of that equation, you see that the discrete logarithm of h, you can now compute it because it's just a sum of discrete logarithms that you already know thanks to the linear algebra step. So a few words now about how should we do to be able to write this equality between products. It's not easy, right? You have a finite field. If I ask how should I do if I want to have an equality between products, I'm not sure the answer is quite obvious. So if you have any idea, I would be very happy to talk about it. But here is a very classical idea. So the classical idea to get relations is the following. First, try to draw such a commutative diagram where all the maps are morphism. So why is it interesting? Because if you start from an element, let's say x, from the set above, E, then going through the two different passes, you will get an equality thanks to commutativity. So this is an equality, but not an equality between products. Then the idea is to define, to fix two small sets, B1 and B2, in the two intermediate sets, E1 and E2. Define the factor basis in J, just saying that it is all the images of B1 and B2 in your group. And then keep only all the elements such that the image of your element in the intermediate set can be written as product of elements of B1 and B2. Why is it interesting? Because if you have something like that, then you know that you have an equality. It's true for any x, so it's true for that special x. Then if I replace it by the former equation, I get something like that. And thanks to the fact that we have morphism, we have now an equality between products. And this is in the group I'm considering. So this is how we do, how we try to write equality between products. So now the question is, what diagram can we draw if we want for G a finite field FP2Z? And the answer is not so obvious. So this is the number field SIEVE. This is a diagram of the number field SIEVE. So let's assume that we have two polynomials f1 and f2 with a common root in FP2Z. We use f1 and f2 to define the two intermediate sets. So we start from polynomials with integer coefficients above, and then we go down to two number fields, just replacing the unknown x by a root of f1 or f2. And then again, we go down to the finite field of p to the n that is defined thanks to that common root theta. And what about the factor basis? Well, we need to define two sets of small elements somehow. So let's say that B1, for instance, is going to be all the prime ideals of a ring of integers with norms smaller than a certain smoothness bound. So it means that we just want prime ideals that are small norms. The same for B2, and at the end, the factor base is just the image of all the elements of B1 and B2 in the finite. And then it's the same. It's almost easy. You just create relation through this diagram. So you just keep elements, you just keep polynomials that lead to elements with more norms in the number field. You create a lot of relations when you have enough. It means when you have almost as many relations as the number of unknowns. You perform the linear algebra step, and then you try to recompute the discrete log of an arbitrary element. So here, this is true for fp to the n in finite field, but you can use the same thing for the prime field fp, just setting n equals to 1, it's okay. So the number field sieve works quite well for fp. And this is what was done to find a discrete logarithm in this 795 bits finite field. If you don't trust me, you can have a look at it. So at the end, what does it look like? So here we are going to have maybe discrete log a little bit bigger than 3. So here is the finite field, the target finite field, fp. They just choose as, so all the integers modulo p, a prime, and here is the prime they were considering. So large prime, quite a large prime. Then they were lucky because g equals to 5 is a very simple generator of the group. So here is the target. And so the question, remember, is, are you able to find an integer x such that g to the x equal to t mod p? And here it's quite simple. There is no polynomial because we are in a prime field. And it took them more than 3,000 core years to get the answer. And the answer is the following. You can really just recompute g to the x and see that it is really t mod p. So it's really hard to find the discrete log, but as soon as you have it, then it's easy to verify that it's true. What about the tower number field sieve? So this is a variance of the number field sieve, and this variance does not work for any finite field. So it's not okay for fp to the n if we know nothing else about p or n. So it helps in this precise case. P is always a prime. I mean, it's a definition because it's a characteristic, it's a prime, and that's it. But n, the extension degree, it can be a prime or equals to 1, whatever you want. But sometimes it's a composite integer. And in that precise case, so for instance, let's say that n is equal to eta times kappa, then in that precise cases, we are able to do something better than just the number field sieve. So the idea is as follows. We will manipulate a little bit the diagram. We are not going to consider polynomials with integer coefficients or rational. We are going to change that rings to another one. So we're going to consider polynomials with coefficients, sorry, in the ring R. And who is R? Good questions. It's So it's a set of all the polynomials with coefficient, with integer coefficients, but looked at modulo another polynomial h, which is irreducible and has a nice property. H should be of degree kappa. So H has somehow a factor of n inside of him. And so now we need to change a little bit the commutative diagram because it's not working anymore. So we are not going to look at polynomials f1 and f2 that share a common root in fp to the n. So this would mean that f1 and f2 share a common irreducible factor of degree n, but fp. But here we just want f1 and f2 to have a common irreducible factor of degree what remains. So what remains here is eta. And you will understand it in a few minutes if you don't right now, why we do that. So now to go down, just look at the elements mod P and mod the irreducible factor, the common irreducible factor of f1 and f2. And this permits to define fp to the n. But I give you a concrete example so that it's easier maybe to follow. So let's have a look at, let's say, fp to the 6, because it's our target, but because it's easy to explain as well. So 6 is equal to 2 times 3. So for that reason, we choose a polynomial h. So the polynomial in iota there, it has degree 3 in iota. And so it means that we need what remains, so degree 2 polynomials that would be the common factor of f1 and f2. And actually, if we set f2, this common factor, so f2 is a degree 2 polynomial that divides f1, then we are able to define fp to the 6 as the set of polynomials with coefficient in fp to the 3 modulo f2. And here fp to the 3 is constructed thanks to the polynomial h. So we need, so this is the reason why it is called tower number field SIEVE, because we need somehow a tower of number fields to define the polynomial, the finite fields. So at the end, it's almost the same. We have some technicalities, but I'm not going to talk about it right now. So at the end, you create a lot of relations thanks to that diagram. You perform linear algebra to find the discrete log of some small elements, and then we compute the discrete log of one average element. Actually, the TNFS is the shorthand for tower number field SIEVE. The fact that this tower variant for NFS was good and worked for composite extension and was already known, but there were both practical and theoretical difficulties to deal with. So I'm just going to talk a bit about two of them. The first one is the fact that in the relation collection for the tower variant for TNFS, we need to enumerate vectors inside an area of dimension that is higher than 6, larger than 6. And previously, we were only, for discrete logarithm purposes, we were only able to enumerate vectors inside rectangles first, and just for dimension 1, 2, and 3. So we needed new tools from Lattice World and to be able to adapt them for our settings. And we even changed the shape of the area where we were looking for the vectors. So now we are using a sphere instead of a rectangle, and it's more efficient. First, because we are sure we have all the vectors inside that area, and then for some reason it's faster as well. And we get better norms if you know about norms. And another difficulty was the fact that sometimes with the tower variant, and by sometimes I mean very often, the diagram produces what we call duplicate relations. What is it? It's when you get twice the same relation at the end, so in your finite field, but coming from two different polynomials in your first set. So this is really important because if you have a lot of informations twice, well, it does not add anything. I mean, you're not going to be able to recover more discrete log or whatever, but it will be hard for your linear algebra step, even sometime to finish, because the matrix will be just too big. So you need to be able to identify beforehand that some polynomials will maybe lead to the same relation at the end. So this was not easy. And at the end, with this tower variant, we were able to find a discrete logarithm in a finite field, so fp to the 6, and fp to the 6 have about 521 bits elements. So if you want to see it, we have a prime, a smaller prime, p, that is like that. And here, let's have a look at how we construct fp to the 6. So fp to the 6 is given thanks to polynomials with coefficient in fp to the 3. And we look at them modulo an irreducible polynomial of degree 2. So that's the reason, because p to the 3 to the 2 is equal to 6. And this polynomial here is exactly f2 in my diagram. So this is how we construct fp to the 6. Keep in mind that we are looking at polynomials with coefficient in fp to the 3, so it means that we are looking at polynomials with an unknown somehow. So we are looking at polynomials with two unknowns, x and iota. That's the reason why for our generator we choose x plus iota, and we were quite lucky because it was a generator. So here is our target. So this is a polynomial of degree 1 in x. That is quite normal because we are looking at polynomials modulo a degree 2 polynomials in x. And you can see that the other coefficients are polynomials with degree 2 at most 2 in iota, which is again quite fine because we are looking at polynomials in fp to the 3, which means that we look at polynomials modulo a degree 3 polynomial in iota, and I hope you are still there. So this is my target, and at the end we were very, very happy to get that discrete logarithm. So maybe you are thinking, okay, but why are you happy? Because 500 bits is smaller than maybe almost 800 bits. And you are right. I mean, indeed, it's smaller. But we were very happy because, well, first, it's the first implementation of this tower variant. And you have to know that with discrete logarithm, sometimes we have huge surprises. I mean, we know the tower variant, but it was not obvious that because of the fact that asymptotically it was a good variant, it was not easy to say if we should get something interesting in practice or not. So we did, and we were very happy for this reason. And then you can remember that this 500 bits finite field was just our first example, like our toy example. So even if it's the largest finite field of extension 6, where discrete log was found, actually it was not so hard. So let me explain why. Well, if we compare with previous relation collection step for non-prime field, So I'm looking at financial with extension. So for instance, fp to the 2, fp to the 4, fp to the 6. So previous relation collection, the last one, took that amount of time. And we were able, thanks to new methods, new algorithms inside, to divide by more than 2 the time spent on that relation collection step. And why is it important? Because with our example, with our algorithm, the relation collection is the most costly step. So here you can see the timing that we got for this discrete logarithm, and clearly you can see that the overall time is almost roughly the relation collection time. Yeah. So at the end, let's have a look at the other computation. We were able to find a discrete log in less than 3 core year, which is very, 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 very low compared to 3,000 core year record computations we are yes. So what does that mean? It means that next time let's target bigger. So that might be maybe it's something we're going to do. I'm not sure yet. Like we have 2 possibilities. Either we can try to see if we spend more time on a finite child of the shape fp to the 6, what can we reach? Or, and maybe it's more interesting, we can have a look at what happens if we target a finite field with a larger extension degree. So for instance, going from 6 to 12. 12 is a composite number, I think it's quite clear. So it means that we can use the Tauro variant of NFS in that finite field. And fp to the 12 is quite interesting because today it is used in the wild. It is used, for instance, in blockchains like Ethereum or Zcash, if you know it. So that should be something maybe to do. And something important too is, maybe a question you have is, why is it so important to really perform such computations? But as I said, the running time of discrete logarithm algorithm is hard to predict first. And then sometimes we have huge surprises. So for instance, in another work, we saw that the estimates for current key sizes and asymptotic analysis do not match. So it means that we have many variants of the number field sieve, and we know about their asymptotic complexities, and it's really helpful because sometimes it will say, okay, have a look at that variant, it should be good or not. But sometimes, because of the fact that the key sizes are not asymptotic, then the estimation we make on how much time should an algorithm last for one target are not fine. So there is something we do not understand well. So that's the reason why record computations provide information for assessing key lifetime. For instance, here is an advice from the NIST. The NIST is a National Institute for Standard and Technology. It's an American institute that tells you, for instance, if you want to use a discrete logarithm, a group, to have the discrete logarithm problem that is safe in it, you should use a group of size 2000 bits. And if you want it to be a bit more secure, you can use a larger one like 3000 bits. So it's important to choose the right key sizes. Why? Because if your key is too large, then it means that you will have needlessly expensive computations, and it's not something that we want. And for sure, if your key is too small, but it means that it is insecure. Someone would be able to break the discrete log in the group, in the related group, and then to read all your messages, for instance. So that's the reason why we really need to perform such computations. And to conclude, well, the directory. So just a few words about public key crypto to see the big picture. So we have 3 problems that are used in practice in the wild, I guess. Factoring. So again, it's for instance for RSA, the problem is to be able to find the factor of a large integer, but we are not really able to do so. It's still a hard problem. We have the discrete logarithm problem. Now you know it. So for instance, in medium and large characteristic finite fields. Something interesting to see is the fact that the key sizes are the same for those problems. And you have the discrete logarithm problem in elliptic curves. That is quite nice because it allows to have smaller key sizes, like 200 bits is quite good. So for that reason, because the discrete logarithm problem is harder in elliptic curves, that is used, for instance, it should be used maybe in your debit card or WhatsApp or whatever. So here it's a variant of Diffie-Hellman, for instance, that is used with elliptic curves. And tomorrow, I mean, as an attacker, like what can we expect? So I think a very natural question is, could we break medium and large characteristic finite fields the same way people did in small characteristic with the same idea? I would say no. Like today I would say no, or maybe not yet, or very not easily, because I know researchers and teams that have tried it for the past 7 years, and currently there is absolutely no sign of an advance this way. So we cannot use the same tools because of the characteristic that is growing too fast. So maybe one day, but not that way or not easily. So I wouldn't say it's something that we can expect for the next years. By the way, the same. Elliptic curves, the discrete logarithm problem in elliptic curves is not concerned by the breakthrough we had in small characteristic finite fields some years ago. So this is safe, not a problem. Maybe something I would like someone to be able to explain that. So there is a link between factoring a large integer and finding a discrete logarithm in a prime field. I mean, for the moment, funny enough, we use a variant of the number field SIEVE to factor numbers too, which is not obvious at first sight. The current records are of the same size. We know to factor a number up to almost 800 bits too. But we cannot really say much more. I mean, we have nothing saying that if we have an algorithm to factor a large integer, then we could derive an algorithm to solve a discrete log problem or something like that. So it's just that for the moment, and because of the algorithms we use, so the number field SIEVE, we have a lot of similarities between those two problems, but nothing is like proven. So it's something I would like to see if you have some ideas again. And so in particular, let's have a look at it. I mean, if you are interested in factoring, then the tower variant I just presented is not working there because it needs an extension, a degree n that is not equal to 1, and think about factoring a large integer almost as a discrete log in a prime field. So that's the reason why actually the tower variant is not working for factoring. I'm not saying that it will not. If you find a way to do it, I would be very happy, but it's not easily working in factoring. But there is a variant that is working in both factorization and discrete log problem in large characteristic finite fields. It's the one called the multiple variant. Very few words. You have a diagram, but instead of looking at two passes, you have multiple number fields inside your diagram. So the idea is we want the polynomials to be more likely to give a relation, because a relation is when a polynomial from the set above, so integer coefficients, can be written as products of small elements in at least two number fields. So you are more likely to have things like that because you have more number fields. That's the idea behind it. And the multiple number field sieve is a little bit as the common number field sieve, let's say 1 year or 2 years ago. It's something we knew, it's something not new. It's something that asymptotically we know the complexity, we know it's good, but we have some obstructions right now. We are not able to, I mean, there is no implementation, no current record using that tools. So it's something that could be done maybe in the near future. And then after, I guess maybe you know that everything here is broken in the quantum world. I mean, everything that we are using in privileged key crypto today could be broken by an adversary, by an attacker that has a quantum computer. So hopefully, it means that there is a whole new crypto to be designed. And I know that you have brilliant researchers in your university working on it, so I'm confident for that. So there is a whole new stuff to work on for cryptographers. But for me, I mean, as an attacker, as someone that is a big fan of DISCRETE, the question is, do we have time? Like, do we have time to target finite fields and to kill them before quantum computers? Not an easy question, and I'm not going to give an answer, sorry. First, because I know very little on quantum computers. But here is the number of quantum bits these computers are able to deal with. So on the left part of my drawing, then you have the hopes for the next 5 years. And on the right part, you see that the number of qubits needed to break current crypto is quite high. So don't forget that it is a logarithmic scale. So still, it's not an answer. I cannot say if we have time or not, but it's not for tomorrow, like tomorrow, but maybe a bit further. And that's it. I can try to.
Well, thank you, Cecile.
Thank you.
Okay, so since it's after 4:30, so let's just ask for one question, and we will leave more discussions in the informal discussion time.
No question.
Yeah, so if you have any question, you can either send via chat or just unmute yourself.
Yeah, sure. I have one.
Yeah.
Hi, thanks for your talk. So when you constructed your tower NFS problem, the representation of the tower field had a specific form. If I were just to give you a problem in FP to the 6 where P was of my choosing and the representation was of my choosing, how upset would you be? Like, how far could you get with that?
It would take a bit more time, but it would be okay, because I will just take your generator, write it in my representation, and then take your arbitrary element, try to find how to represent it, and then work in my representation. It's something we do sometimes. So
Okay.
I would be upset, like, because I would need to implement something a bit more, but it's not as hard as finding discrete log. So.
Okay.
It's a good question, actually.
Okay, thank you. So yeah, so let's just amuse ourselves and then give a pause and thank Cecile for the nice talk, and we'll have more discussions in informal. So let me stop recording now.